All right, welcome to section 4.8. What we're talking about in 4.8 is just some applications of trig functions. So different ones that sometimes have to do with context of a problem, sometimes don't. So starting off with something just straight up geometric. If we say to solve the right triangle, what we're talking about when we're talking about solving a right triangle is finding all of the missing pieces of information. So if I set up a right triangle, and I know that this must be angle A because it's 90 degrees, side A, which is the side across from it, is length 8. B is 37 degrees, which you can call either of these angles. And I'll just call this one C. Here I have little c and little b, the sides. If I want to solve the right triangle, I want to find all three pieces of missing information. So the easiest to find is going to be angle C. Angle C, the three angles of a triangle always add up to 180. So angle C is 180 minus the 90 degrees from angle A minus the 37 degrees from angle B. And when I subtract that, I'm going to get angle C being 53 degrees. For side C and side B, now is when you're going to use some trig. So I know this is 53 degrees. If I look at angle 37, I can say that the sine of 37 degrees, sine of 37 degrees is opposite over hypotenuse. So that's B over 8. And if I solve for B, I get B equals 8 sine 37 degrees. When you're putting this in a calculator, it's in degree mode because it says degrees. So you get B is equal to, let me look at 4.81. On the other hand, if I want to solve for side C, you have some flexibility in this. So some people are like, okay, I'll do cosine 37, which you're more than welcome to do. You could also just do sine again, but now say, okay, I'm going to do the sine of 53 degrees. And if I do the sine of 53 degrees, I get C over 8. So C equals 8 sine 53, which if you were to put into your calculator, you'd get C equaling approximately 6.4. So this right triangle is solved. Doing another example of that, the first thing that you're going to recognize is you have this weird minutes and degrees. So I'll walk through the explanation of what we do with that. Let me just label this triangle first. We're going to call this A, B, C. We know that A is 90 degrees. We know that side C is 12. And we know that C is all that. But first we want to talk about the conversion of this. So here we have minutes and seconds. When we talk about seconds, that's out of 60. So this is 37 sixtieths of a single minute. 37 sixtieths, if you were to put that into a calculator, you get 0.616 repeating. So this is really like 62 degrees and 10.616 repeating minutes. Well, this still doesn't help us because that's minutes. So what you can do is take that out of 60, since there are 60 minutes in a degree. When I do that, I'm then going to get 62.177 degrees. So this 10 minutes and 37 seconds, that's really just saying 0.177 degrees. It's just a different sort of notation and way of thinking about that. Again, in that conversion, you do the seconds over 60, add that to your minutes. So 37 sixtieths gives me this. I added that to 10, and then do that over 60 to convert it to degrees. So I know that angle C is 62.177 degrees. The easiest thing to solve here is angle B, which is 180 minus 90 minus 62.177. And when I subtract that, I get a 27.823 degree angle. Next, I want the two sides. So we have side B and side A. I'll use the sine of angle C. So sine of 62.177 degrees equals 12 over A. opposite over hypotenuse. That means A is equal to 12 over sine 62.177. And if I do 12 over 62.177, I get 3.569. Sorry, 13.569. I can't read my own handwriting. On the other hand, if I want side B, I could do the cosine of this. So cosine 62.177 equals adjacent over hypotenuse. Now that, you might want to avoid that. So I'm going to switch my mind here. The reason I'm going to try to avoid that is because that is going to use a rounded answer in order to get an answer. And we're already using one rounded answer. We're using a rounded angle. And then we're going to also use a rounded side. And that might be off by a little bit. So let's change this and let's say, you know what? I want to use that 12 because that's nice. It's an integer. So I'll use tangent 62.177. Equals opposite over adjacent, so 12 over b. That gives me b equals 12 over tangent 62.177. So b is approximately 6.333. So that's solving a right triangle. Essentially, find all of the missing information for that right triangle. In the next problem, find the length of the altitude and congruent sides of an isosceles triangle whose base is 6 units long and base angles are 38 degrees. So I'll start by drawing this and say, okay, this is an isosceles triangle. Isosceles meaning those are congruent and these are the congruent. The whole base is 6 units long. And what you learned about an isosceles triangle last year is that this altitude in an isosceles triangle will split the base. So each of these sides is 3. It also tells us that the base angles, which are the congruent angles, are 38 degrees. So all I personally am going to look at is this triangle. Okay, well, sort of missed that red line a little bit. So now if I'm looking at just this red angle, if I called this side A and side C, I'm looking for the length of the altitude and the congruent side. So altitude, congruent side. If I want that altitude, I can look at this 38 degrees and say I have the opposite and adjacent. So that would be tangent 38 equals A over 3. So A equals 3 tangent 38. When I put that into my calculator, 3 tangent 38, again in degrees, I get 2.344. If I want C, I don't want to necessarily use this because I just rounded it. So instead I'll look to use the adjacent side and hypotenuse, which means I'll do cosine of 38 degrees equals 3 over C. So C is equal to 3 over cosine 38. And 3 over cosine 38 gives me approximately 3.807. All right, then moving into a contextual problem, so something that has a word or scenario with it. A shadow of a length L is created by a 325-foot tall building. As the sun rises, the shadow decreases in length. Write an equation for the L, the shadow length, in terms of theta, the angle of elevation to the sun from the top of the building. So if I draw this wonderful triangle, and I'm moving something else. Let's try that again. If I draw this wonderful triangle here, we have a height of 325 feet. L represents the shadow length. Well, L will be down here then. A lot of people put L as the hypotenuse, but if you think about like where does a shadow really get cast, it's cast across the ground. It says that theta is supposed to represent the angle of elevation to the sun from the top of the building. So when we're talking about that, you sort of have to change this picture a little bit, but don't worry, we're not going to have to erase. So here's the top of the building. What we want theta to be is this angle, the angle of elevation from the top of the building to the sun. But if you remember a little bit of your geometry, this angle is going to be the same as this angle. I believe that's corresponding sides of a transversal. So theta here is the same as theta here. And if I want to write an equation, I have the relationship of an opposite side and adjacent side. So tangent of theta equals 325 over L. It asks for an equation for L in terms of theta. What that means is you need this to be L equals. So I need to solve this for L. That gives me L equals 325 over tangent theta. Over tangent is the same as cotangent. Last, a flagpole sits atop a building. You stand 100 feet from the base of the building. So let's draw our building. So here I am, standing 100 feet away from a building. A flagpole sits atop that building. So here I've got my flagpole. The angle of elevation to the top of the building is 28 degrees. The angle of elevation to the top of the flagpole, ooh, that did not go anywhere where it was supposed to. So the angle of elevation to the top of the flagpole is 39 degrees and 45 minutes. Again, you think of that as over 60, so that's 0.75. So this is really 39 3/4 or 0.75 degrees. That represents this larger angle, 39.75 degrees. We want to find the height of the flagpole, so I'll call this H. Now you can notice here I have two right triangles. I have this one, let's call this Y, and I have this entire right triangle, which I'll call X. So if I wanted to find just Y, the height of the building, I have the opposite side and adjacent side, so I would say tangent 28 equals Y over 100. So Y equals 100 tangent 28. If I wanted X, the height of the building and flagpole, I would still use tangent, but now I'd have 39.75 equals the opposite side here would be all of X over 100. So X equals 100 tangent 39.75. If I'm looking for just H, what H really represents is the distance between X and Y. It's what I get if I subtract X minus Y. Well, I have an equation for X and an equation for Y. So I'll do H is equal to X, 100 tangent 39.75, minus Y, 100 tangent 28. When I put that into my calculator, you'll get roughly 30 feet. So this just goes through some different applications. Word problems obviously can be a little bit tricky, but I always recommend drawing that picture first and then trying to think of what trig relationship relates all of these different things. Otherwise, get started on some of that 4.8 book work, end of the chapter, exciting.